There is a place in the constellation Sagittarius, roughly 26,000 light years from the chair you are sitting in, where 4 million times the mass of our Sun has been compressed into a region smaller than the distance between Earth and the Sun. We have a photograph of it, not an artist's impression, not a simulation. A real image, assembled from radio telescope data, collected simultaneously across 8 observatories on 4 continents. A planet-sized instrument trained on the center of our own galaxy, capturing the silhouette of an object from which nothing, not light, not heat, not information of any kind, has ever escaped. We took its picture. We named it Sagittarius A. And then we spent the next several years arguing with increasing urgency about whether everything we thought we understood about physics might be wrong. Not approximately wrong, not wrong in the margins, wrong at the foundations. Because the black hole is not just a strange object. It is the place where the 2 greatest theories in the history of science, general relativity and quantum mechanics, walk calmly up to each other and, in full view of anyone with the mathematics to watch, catastrophically contradict each other. The black hole is where physics breaks, and nobody, not a single physicist alive today, knows how to fix it. If you enjoy videos that take the deepest unsolved problems in science and work through them honestly, that do not simplify into false comfort, but instead sit with the genuine difficulty, I genuinely appreciate it if you hit that like button. Subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about why black holes trouble scientists is that the trouble is about the black hole itself, about its interior, its singularity, its event horizon. People assume the fear is existential. These objects are so extreme that they scare us the way abysses scare us. That framing is wrong. Not wrong as a feeling, the awe is real and appropriate, but wrong as an explanation. The reason black holes genuinely disturb physicists at the deepest level is not what black holes do to matter, it is what black holes do to information, to the concept of information itself, to the principle so fundamental that it underlies every equation in physics, every calculation ever performed, every prediction ever made, that information cannot be destroyed. Black holes appear to destroy information, completely, irreversibly. The implications of this, if true, would not merely add a new chapter to physics, they would require rewriting physics from the foundations up. That is what keeps physicists awake, not the darkness of the black hole, the darkness of not knowing whether the most basic assumption in all of science holds when you need it most. To understand this, you need to understand 3 things: what a black hole actually is and how it forms, what the information paradox is and why it arose, and what the current state of the attempted solutions tells us about where physics stands today. Each of these is a story in its own right. Together, they form the most consequential unsolved problem in fundamental physics, and one of the most consequential in all of science. A problem whose resolution will require either quantum mechanics or general relativity to be wrong, or both, or something entirely new that we do not yet have words for. Begin with the black hole itself, and with the history of how an idea that was once considered so absurd it was not taken seriously became the most studied object in theoretical physics. The concept of a black hole, or something very like it, was first proposed not by a 20th century relativist, but by an 18th century English clodagh. John Michell, in 1783, noted that if a star were sufficiently massive and sufficiently compact, the escape velocity from its surface would exceed the speed of light. In Michell's Newtonian framework, light was assumed to be composed of particles subject to gravity, and the escape velocity calculation was straightforward. A star with the same density as the Sun, but a radius 500 times larger, roughly corresponding to the mass of a small galaxy, would have an escape velocity equal to the speed of light. All light emitted from such a body would be made to return towards it, Michell wrote, with a calmness that belies the extraordinary nature of the claim. Such a body would be invisible. It would be detected only through its gravitational influence on other objects. Pierre-Simon Laplace made the same calculation independently in 1796, coining the phrase corps obscurs, dark bodies. These early dark bodies were essentially Newtonian black holes, invisible because light could not escape, detectable only gravitationally. But the Newtonian framework they rested on was not the right framework for objects at the speed of light, and the concept quietly faded from serious discussion for over a century. It returned in December 1915. Albert Einstein had just published his field equations of general relativity, 10 coupled nonlinear partial differential equations relating the curvature of space-time to the distribution of mass and energy within it. The equations were extraordinarily complex, and Einstein himself doubted they had exact solutions. Within weeks, a German physicist and astronomer named Karl Schwarzschild, who was serving on the Russian front in World War I and would die there of illness the following spring, had found the first exact solution. The Schwarzschild solution described the geometry of space-time outside a spherically symmetric mass, a planet, a star, any perfectly round object in empty space. It was an exact, closed-form solution, something Einstein had not expected to exist so quickly, and he was delighted. But the solution contained something troubling. At a specific radius from the centre of any mass, now called the Schwarzschild radius, the mathematical description of the space-time geometry became pathological. The metric tensor, which describes the space-time geometry, developed what appeared to be a singularity. Certain components blew up to infinity or divided by zero, as if the equations were breaking down. For a body with the mass of the Sun, the Schwarzschild radius is approximately 3 kilometers, far smaller than the actual radius of the Sun, so the Sun is not actually at risk of exhibiting this behavior, since the exterior solution only applies outside the surface, and the Sun's surface is much larger than 3 kilometers. For the Earth, the Schwarzschild radius is about 9 millimeters, roughly the size of a marble. As long as real physical objects are larger than their Schwarzschild radius, the troubling behavior is hidden inside the object and does not affect the external spacetime. But what if an object were compressed below its Schwarzschild radius? For decades, physicists were divided on whether this was physically possible, and many, including Einstein himself, argued that it was not. Einstein published a paper in 1939 arguing that a collection of particles in circular orbits could never be compressed inside the Schwarzschild radius, and concluding that the Schwarzschild singularities do not exist in physical reality. He was, in this specific argument, wrong, though for reasons that took another 20 years to fully work out. The key insight came from J. Robert Oppenheimer and his student Hartland Snyder in 1939, the same year as Einstein's paper, and published in the same journal, Physical Review. Oppenheimer and Snyder showed that a sufficiently massive star, at the end of its life, could not avoid collapsing within its Schwarzschild radius, and that an external observer watching the collapse would see the collapsing surface approach the Schwarzschild radius asymptotically, getting ever closer but never quite reaching it. The clock of the surface appearing to slow due to gravitational time dilation. The collapse, from the outside view, takes infinite time. The collapsing material itself, however, reaches the Schwarzschild radius in finite proper time, the time measured by a clock on the surface, and then continues to collapse inward. There is a disconnect between what the outside observer sees and what the infalling observer experiences. The infalling observer crosses the Schwarzschild radius in finite time. The outside observer never sees this happen. The Schwarzschild radius is the event horizon. The event horizon is not a physical surface. It is not a boundary made of any material, not a place where matter accumulates or collides. It is a mathematical boundary in space-time, a surface of no return, defined by the condition that anything crossing it, whether matter or light, cannot subsequently escape. The name captures the concept precisely. It is the horizon of events, the boundary beyond which no event can send a signal to the outside universe. Cross it, and you are causally disconnected from everything outside. You can send no message, no signal, no particle, no photon. Not because the physics of signaling fails inside locally. Physics proceeds normally, and you feel nothing special as you cross, but because the geometry of space-time inside the horizon is confused such that all future directed paths lead inward toward the center. The future, inside a black hole, points inward. You cannot travel to the future without traveling inward. Escaping is not hard. Escaping is geometrically impossible, in the same sense that traveling to yesterday is geometrically impossible in the external universe. This is worth sitting with for a moment, because it is the most common point of confusion about black holes. The event horizon is not a wall. It is not a barrier made of anything. It is a geometric fact about the causal structure of space-time, about which regions of space and time can communicate with which other regions. Think of it this way. Imagine you are standing on the bank of a river, and upstream there is a waterfall. If you swim upstream fast enough, you can escape the pull of the current and make it to safety. If you swim slowly, you'll be pulled over the falls. There is a critical point, some distance upstream from the edge, at which the current exactly equals your swimming speed. Closer than that point, no matter how hard you swim, you fall. That critical point is the event horizon of the waterfall. Beyond it, downstream, all paths lead over the edge. The horizon is defined not by any physical feature of the water at that point. The water looks the same there as anywhere else, but by the geometry of the flow. The event horizon of a black hole is the same, defined by the geometry of space-time, invisible to a local observer, but absolutely real in its consequences. How do black holes actually form? Not from any single mechanism, but from several, operating at different mass scales and producing different types of black holes. The most common formation pathway is the death of a massive star. A star between roughly 20 and 100 times the mass of the Sun, at the end of its nuclear burning life, undergoes a core collapse supernova. The iron core, the inert, fusion-exhausted core, that forms after millions of years of nuclear burning, collapses in a fraction of a second, when it can no longer support itself against gravity. In most cases, this collapse produces a neutron star, a sphere of neutron-rich nuclear matter, roughly 20 kilometers across, held up by neutron degeneracy pressure and the strong nuclear force. But if the collapsing core is sufficiently massive, above approximately 3 solar masses, neutron degeneracy pressure cannot halt the collapse. The neutron star that would have formed instead continues to collapse, inexorably, through its own Schwarzschild radius, and a black hole forms. This threshold, the maximum mass of a stable neutron star, is called the Tolman-Oppenheimer-Volkoff limit, and its exact value depends on the equation of state of nuclear matter at extreme densities, which is itself an unsolved problem in nuclear physics. Current estimates place it between roughly 2.3 and 2.9 solar masses. Stellar mass black holes, formed this way, range from roughly 5 to roughly 100 solar masses. Hundreds of millions of them are estimated to exist in our galaxy alone, the graveyard of all the massive stars that have died over the Milky Way's 12 billion year history. Most of them are dark and silent, drifting through the galaxy without visible companions, detectable only if they happen to be in binary systems, where they pull mass from a companion star and produce X-ray emission, or if they happen to pass in front of a background star and produce gravitational microlensing. The few thousand identified so far are the ones that happen to be conveniently situated for detection. The full population is invisible. Then there are intermediate mass black holes, objects in the range of hundreds to hundreds of thousands of solar masses, whose formation mechanism is debated. They might form from the mergers of stellar mass black holes in dense star clusters. They might form from the direct collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. They might form from the collapse of the first generation of stars, the population 3 stars. There are the supermassive black holes, the giants at the centres of galaxies. Sagittarius A has 4 million solar masses. The black hole at the centre of M87 has 6.5 billion solar masses. The most massive known black hole, at the centre of the galaxy TOM 618, has approximately 66 billion solar masses, a mass so large that its Schwarzschild radius is about 13 times the distance from Earth to Neptune. How objects this large formed in the early universe, when the universe was only a few 100 million years old, and there had not been enough time for ordinary stellar evolution to produce them through sequential mergers, is one of the most pressing unsolved problems in astrophysics. Quasars, the luminous distant objects powered by accretion onto supermassive black holes in the early universe, show that billion solar mass black holes existed when the universe was less than 1 billion years old. The formation mechanism for these early giants is unknown. They should not exist by our current models of black hole growth. They do exist. The models are missing something. John Wheeler, the physicist who did more than anyone to make black holes a serious object of study in the 1960s, coined the term black hole in 1967, a name that stuck immediately because it captured both the physics and the visceral quality of the concept. Before Wheeler's advocacy, the objects were called completely collapsed stars or frozen stars. The latter because, from outside, the collapse appears frozen at the event horizon. Wheeler insisted they were not frozen. They were complete. They were holes in the observable universe. Black holes. The 1960s and 1970s were the golden era of black hole theory, a period of extraordinary intellectual productivity in which the basic properties of black holes were established with mathematical rigour. Roy Kerr found the exact solution for a rotating black hole in 1963, a solution far more complex than Schwarzschild's, describing the twisted, dragged space-time around a spinning mass, and applicable to every real astrophysical black hole, since all real black holes rotate. Roger Penrose proved in 1965 that singularities, regions of infinite density and infinite space-time curvature, are not an artifact of the unrealistic assumption of perfect spherical symmetry, but are a generic feature of gravitational collapse. Any sufficiently massive collapsing object will develop a singularity, regardless of its exact shape or initial conditions. Stephen Hawking and Penrose together proved a series of singularity theorems that established this result in full generality. The singularity inside a black hole is not a mathematical curiosity. It is real, it is inevitable, and it is the place where general relativity announces, loudly and clearly, that it has reached the boundary of its own validity. But before we reach the singularity, something extraordinary happened in the theoretical landscape of the early 1970s. Black holes acquired thermodynamics. I would all know what the science of Earth's powers could possibly be possible. I would not all know how, the reason. They became, in a precise mathematical sense, thermodynamic objects, objects with temperature, with entropy, with a full set of laws governing their thermodynamic behavior. And this development, which began as a curiosity and became a revolution, is where the seeds of the information paradox were planted. In 1972, a young graduate student named Jacob Bekenstein made a proposal that was initially received with deep skepticism. Bekenstein argued that a black hole must carry entropy, not just mass and spin, but entropy, the thermodynamic quantity that measures disorder, the quantity that always increases in any spontaneous physical process. His argument was based on a thought experiment. Suppose you drop a highly entropic object, a gas of particles in a state of high disorder, into a black hole. Once the object has fallen in, the external universe has lost a certain amount of entropy. The entropy of the dropped object has vanished behind the horizon. If the total entropy of the universe cannot decrease, which is the second law of thermodynamics, arguably the most powerful and universal law in all of physics, then the black hole itself must carry entropy. The entropy cannot simply vanish. It must be carried by the black hole. Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon. Not the volume, the area. For a Schwarzschild black hole, the event horizon is a sphere, and the area is 4 pi times the Schwarzschild radius squared. The entropy is proportional to this area. This seems counterintuitive. Entropy usually scales with volume, with the number of degrees of freedom contained in a system, and a larger system has a larger volume, but not necessarily a larger area. The Bekenstein's proposal was radical. It said that the number of degrees of freedom of a black hole, the number of distinct quantum states it could be in, scales with the area of its horizon, not the volume of its interior. This is the holographic principle in embryonic form. If the information content of a black hole is stored on its horizon, on its two-dimensional surface, then the black hole is, in a sense, a hologram. A three-dimensional it's about 5 to 10 minutes, and it's about 1 to 5 minutes. This idea, later developed into the holographic principle by Gerard 't Hooft and Leonard Susskind, has become one of the central organizing principles of quantum gravity research. It underlies the ADS-C50 correspondence. It informs the ER equals EPR conjecture. It is the idea that, at the deepest level, the universe is lower dimensional than it appears, that three-dimensional space is a kind of projected hologram of a two-dimensional quantum description. Bekenstein's proposal was initially resisted, and for a specific reason. If a black hole has entropy, it must have temperature, because temperature and entropy are thermodynamically linked. But a black hole with temperature must radiate, and a black hole that radiates is not black. It emits something. This seemed impossible. Black holes were defined by the inability of anything to escape. How could a black hole radiate? Hawking initially opposed Bekenstein's proposal on exactly these grounds. Then, in 1974, he did the quantum mechanical calculation of what fields do near the event horizon, and found that Bekenstein was right. Black holes do radiate. The Hawking radiation was the confirmation of Bekenstein's conjecture, and its temperature, the Hawking temperature, was precisely the temperature that Bekenstein's entropy formula demanded. The two calculations, done independently from different directions, agreed perfectly. The Bekenstein-Hawking entropy formula, S equals A divided by 4 times Planck length squared, is now considered one of the most important equations in theoretical physics, connecting area A, geometric quantity, from general relativity, entropy, a thermodynamic quantity, and the Planck length, a quantum gravitational quantity. It is a formula that belongs simultaneously to 3 different theories and is consistent with all of them. It is a hint, a very strong hint, about the structure of quantum gravity. The 4 laws of black hole thermodynamics, developed during this period, are a perfect mathematical analogue of the 4 laws of ordinary thermodynamics. The 0th law of black hole mechanics states that the surface gravity of a stationary black hole is constant over the event horizon, in analogy with the 0th law of thermodynamics, which states that temperature is constant throughout a system in thermal equilibrium. The 1st law relates changes in the black hole's mass to changes in its area and angular momentum, in analogy with the 1st law of thermodynamics, which relates changes in internal energy to heat and work. The 2nd law, Hawking's area theorem, proven in 1971, states that the area of a black hole's event horizon can never decrease in any physical process, in analogy with the 2nd law of thermodynamics, which states that entropy never decreases in an isolated system. The 3rd law states that you cannot reduce the surface gravity of a black hole to 0 in a finite number of steps, in analogy with the 3rd law of thermodynamics, which states that absolute 0 temperature is unattainable. Hawking's area theorem is a theorem of classical general relativity. It holds as long as general relativity is valid and the matter entering the black hole satisfies reasonable energy conditions. Its analogue with the 2nd law of thermodynamics was initially considered a mathematical curiosity. Then Bekenstein identified the horizon area with entropy, and Hawking discovered the Hawking temperature, and the analogy became an identity. The area theorem is the 2nd law of thermodynamics. For black holes, the entropy is real, the temperature is real, the thermodynamics is real. But here is the crack. The 2nd law of thermodynamics, in its usual formulation, holds because the systems it describes have a huge number of microscopic degrees of freedom, molecules in a gas, spins in a magnet, and entropy is a measure of how many microscopic configurations correspond to the same macroscopic state. Hot objects radiate because their microscopic degrees of freedom are in high energy states that can couple to the radiation field and emit photons. The temperature is a measure of the energy in those microscopic degrees of freedom. For ordinary matter, we know exactly what the microscopic degrees of freedom are: atoms, electrons, quarks. We can, in principle, derive thermodynamics from quantum mechanics, starting from the microscopic description and building up to the macroscopic one. This is statistical mechanics, one of the triumphs of 19th and 20th century physics. For black holes, Bekenstein identified the entropy with the area, and Hawking calculated the temperature, but nobody knew, and to this day nobody has fully answered, what the microscopic degrees of freedom of a black hole are. What is the microscopic description that underlies black hole thermodynamics? What are the quantum states that the black hole entropy is counting? In ordinary statistical mechanics, the entropy is the logarithm of the number of microscopic configurations consistent with the macroscopic state. S equals K log W. What are the W configurations for a black hole? Where are they? Are they on the horizon? In the interior? In some quantum gravitational structure that replaces the classical geometry? This question, the microscopic origin of black hole entropy, is one of the central problems of quantum gravity, and it is the direct parent of the information paradox. If the entropy of a black hole counts the number of distinct quantum states, then those quantum states carry the information about what fell in. When the black hole evaporates, those quantum states must somehow be reflected in the outgoing radiation. If the radiation is exactly thermal, the quantum states are not reflected. The information is lost. If the radiation is not exactly thermal, but carries subtle quantum correlations encoding the interior state, the information is preserved, but then the Hawking calculation is not exactly right, and something has to modify it in a way that is not yet understood. A singularity is not a place. It is the absence of a place. In general relativity, a singularity is defined as a region where the equations of the theory break down completely, where the curvature of space-time becomes infinite, where physical quantities like density, tidal force, and temperature diverge to infinity, and where the theory has nothing meaningful to say about what happens. The singularity is not a point in space where something extreme occurs, and then the physics continues. It is the termination of physics itself within the framework of general relativity. The laws of physics, as formulated in general relativity, simply stop applying there. Time ends there. Space ends there. The geodesics, the trajectories of freely falling particles, reach the singularity in finite proper time, and then cease to exist as mathematical objects. The infalling observer does not encounter anything at the singularity. The infalling observer stops existing as a continuously evolving entity described by the equations. This is what Penrose and Hawking proved. Not that something extreme happens at the centre of a black hole, that the laws of physics as written terminate there. Any theory that predicts its own termination is, by that fact alone, incomplete. General relativity is incomplete. It tells us, from within its own mathematics, that there is a regime, the black hole interior, and especially the similarity, where it cannot be trusted. A theory that announces its own incompleteness is not wrong in the ordinary sense. It is correct in the regime where it has been tested and certified, but it is pointing from the inside at a region beyond its reach. The black hole singularity is general relativity's confession that something else, something beyond general relativity, must take over at extreme densities. The natural candidate is quantum mechanics. More precisely, quantum gravity, a theory that unifies general relativity's description of curved spacetime with the quantum mechanical description of matter and energy. Such a theory does not yet exist. We have quantum field theory, which describes the behavior of matter and energy in flat or weakly curved spacetime with extraordinary precision, confirmed to more decimal places than almost any other measurement in science. We have general relativity, which describes the geometry of curved spacetime with extraordinary precision, confirmed by solar system tests, by gravitational wave observations, by pulsar timing, by the imaging of black holes. But the two theories are not compatible. Not incompatible in the sense that they make contradictory predictions for any experiment performed to date. They operate in different regimes, and to date those regimes have not significantly overlapped. Incompatible in the sense that the mathematical structures underlying them are fundamentally different. And when you try to combine them naively to apply quantum field theory in the strongly curved spacetime of a black hole interior, the result is either intractable or nonsensical. The infinities that appear when you try to compute quantum corrections to gravity near a singularity cannot be removed by the standard procedures that work in other quantum field theories. The calculation breaks down. The result is nonsense. You need a new theory. And here is where the fear deepens. Because it is not only the singularity that causes trouble, it is the event horizon. And the trouble at the event horizon is in some ways more disturbing than the trouble at the singularity. Because the event horizon is not a place where the curvature is infinite. It is a perfectly ordinary region of spacetime in terms of local physics. A massive black hole, the supermassive black holes at the centers of galaxies, with masses of millions or billions of solar masses, has an event horizon so large that the tidal forces there are gentle. An observer falling through the event horizon of a billion solar mass black hole would feel nothing special. No wall, no barrier, no signal. The space-time curvature at the horizon of such a black hole is comparable to, or even gentler, than the curvature of the Earth's surface. And yet the physics there, specifically the quantum physics there, is the source of the most profound crisis in modern theoretical physics. That crisis has a name: the black hole information paradox. And it begins with a discovery by Stephen Hawking in 1974 that was intended to be a triumph, but turned out, upon examination, to be a catastrophe. Hawking was applying quantum field theory, the quantum mechanical description of fields, to the curved spacetime near a black hole, treating the spacetime geometry as a fixed classical background, and asking what quantum fields defined on that background do. This is an approximation. It is not the full theory of quantum gravity, which does not exist, but a semi-classical calculation that should be valid when the spacetime curvature is small and the quantum corrections to the geometry itself can be neglected. In this approximation, he calculated how quantum fields behave near the event horizon of a black hole. What he found was astonishing. Black holes radiate. Not by emitting matter from inside, nothing crosses the event horizon outward, but by a quantum process at the horizon itself, the vacuum of quantum field theory is not empty. It is a seething sea of virtual particle pairs, particle-antiparticle pairs that pop into existence from the vacuum, exist briefly, and annihilate. This is not a metaphor, it is a real quantum mechanical phenomenon, confirmed by laboratory measurements of the Casimir effect, in which two parallel conducting plates attract each other because the quantum vacuum fluctuations between them are restricted compared to those outside, producing a measurable pressure. Near a black hole's event horizon, a virtual pair can form with one member just inside the horizon and one member just outside. The member outside can escape to infinity. The member inside cannot. It falls toward the singularity. The net effect is that the black hole loses a tiny amount of energy equal to the energy of the escaping particle, and a real particle, not a virtual one, departs the black hole and travels outward. This is Hawking radiation. The temperature of the Hawking radiation, called the Hawking temperature, is inversely proportional to the mass of the black hole. A solar mass black hole radiates at a temperature of approximately 60 nanokelvins, 60 billionths of a degree above absolute zero, so cold that it would be completely overwhelmed by the ambient cosmic microwave background radiation at 2.725 Kelvin, and in practice, undetectable. A black hole the mass of a mountain, a few times 10,012 kilograms, roughly the mass of a small asteroid, would radiate at a temperature of around 10,200 Kelvin and would explode in a burst of gamma rays visible across the galaxy. But such a black hole, if it were to exist, would have formed only in the extreme conditions of the early universe and would have long since evaporated. Stellar mass and supermassive black holes will radiate for unimaginably long times. A solar mass black hole will take approximately 2 by 10 to the power of 6 years to completely evaporate through Hawking radiation, a number so much larger than the current age of the universe, 1.4 by 10 to the power of 10 years, that the ratio between them is roughly the same as the same ratio between the diameter of the observable universe and the diameter of a proton. Despite its practical inaccessibility, Hawking radiation is one of the most important theoretical results in modern physics, because it connects three of the great frameworks: quantum mechanics, general relativity, and thermodynamics in a single calculation. And it immediately raised a question that Hawking himself recognized and that has haunted theoretical physics ever since. When a black hole forms from a collapsing star, the collapsing matter is in a specific quantum state, a specific precise configuration of particles, fields, and quantum correlations. The black hole that forms from this collapse has, in the Hawking radiation picture, no information about the internal state of the collapsing matter. The Hawking radiation is thermal. It has the spectrum of a perfect black body at the Hawking temperature, which contains no information about what fell in. A black hole formed from the collapse of a star is indistinguishable, in terms of its Hawking radiation, from a black hole formed from the collapse of an equal mass of anything else. An equal mass of antimatter, of radiation, of a precisely arranged quantum computer, of a rock. The radiation emerging is the same. The information about what fell in, the quantum state of the original matter, is not encoded in the outgoing radiation. When the black hole has completely evaporated, when it has radiated all its mass energy away as Hawking radiation and nothing remains, What has happened to the quantum state of the original matter? In quantum mechanics, the evolution of quantum states is governed by the Schrödinger equation or its relativistic generalizations, and this evolution is unitary. It is reversible, information preserving. The initial quantum state of any closed system determines all future states, and from any future state you can in principle reconstruct all past states. Information is conserved. This is not an empirical observation that could be falsified by some future experiment. It is a mathematical property of the equations of quantum mechanics. Unitarity is the backbone of quantum theory. It is what makes quantum mechanics internally consistent. It is what ensures that probabilities always add up to 1. Without unitarity, quantum mechanics is not a theory. It is a collection of equations without a coherent physical interpretation. Hawking's calculation implied that black hole evaporation is not unitary. The initial quantum state, the specific configuration of the collapsing matter, is a pure quantum state, a state with a definite, complete quantum description, with no randomness or ignorance about it. The final state, after complete evaporation, is a thermal state, a mixed state, with the randomness and ignorance characteristic of a system at a definite temperature, but without a precise quantum description. In quantum mechanics, a pure state can never evolve into a mixed state under unitary evolution. It is forbidden by the mathematics. But Hawking's calculation says it does. A pure state goes in, a mixed state comes out. The evolution is not unitary. Information is destroyed. Not lost, not hidden, destroyed. This is the information paradox. Hawking published this argument in 1976 and was explicit about the implication: either quantum mechanics or general relativity must be modified. One of the two most successful theories in the history of physics had to be wrong in a regime that, while not yet experimentally accessible, was physically real. Every black hole in the universe, as it forms and eventually evaporates, destroys information. If Hawking was right, the fundamental reversibility of physics, the principle that the past is encoded in the present, but the universe's history is not erased, fails whenever a black hole forms and evaporates. The physics community did not accept this quietly. The information paradox immediately became one of the most debated problems in theoretical physics, a debate that has continued for nearly 50 years, grown more intense rather than less, and has drawn in virtually every major figure in fundamental physics at one time or another. Hawking himself debated John Preskill and Kip Thorne in 1997, with all parties betting on the outcome, a bottle of fine wine for the winner. The bet concerned whether information was lost. Preskill bet it was not. Hawking bet it was. Thorne bet it was. In 2004, Hawking conceded the bet. He announced at a conference in Dublin that he had developed a new argument based on path integral methods in quantum gravity, that information was not permanently lost, that the black hole evaporation process was in fact unitary after all, and that the information was returned to the universe in the Hawking radiation, albeit in a highly scrambled and practically unrecoverable form. He gave Preskill, an encyclopedia of baseball, the agreed prize. Thorne refused to concede, arguing that Hawking's 2004 argument was not rigorous enough to settle the question. Thorne's skepticism was, in retrospect, justified. The argument Hawking presented in 2004 convinced very few specialists. The information paradox did not end in Dublin. It intensified. But Hawking's concession, even if unproven, pointed toward a concept that has become central to modern discussions of the information paradox: quantum information scrambling. The idea is that the information about what fell into the black hole is not destroyed, it is scrambled. mixed up, redistributed, encoded in the quantum correlations between Hawking photons in a way that is exponentially complex to decode. Not lost. Hidden. The black hole, in this picture, is not a shredder of information, but an extraordinarily efficient scrambler, a physical system that takes any input quantum state and rapidly distributes its information across all of its degrees of freedom, encoding it in global correlations that no local observation can decode. The scrambling time, the time it takes the black hole to fully scramble the information of an infalling object, has been estimated to be proportional to the black hole mass times the logarithm of the black hole entropy in Planck units. For a solar mass black hole, this is extraordinarily short, fractions of a millisecond. The black hole scrambles information nearly as fast as any physical system can. In fact, black holes are conjectured to be the fastest scramblers in nature. Fastest scramblers, bound, proposed by Patrick Hayden and John Preskill in 2007, states that black holes saturate the bound on the scrambling rate set by the laws of quantum mechanics. No physical system can scramble information faster than a black hole does. This conjecture has a remarkable implication. Hayden and Preskill showed that if the black hole is already emitted more than half its information in early Hawking radiation, if we are past the page time, then an infalling observer who jumps in carrying a message can have that message decoded from the Hawking radiation extremely quickly after they cross the horizon, in a time roughly proportional to the logarithm of the black hole entropy, which is exponentially shorter than the black hole evaporation time. The information escapes almost immediately after it enters. Not because it was never captured, it was, but because the scrambling is so efficient that the correlation between the infalling information and the outgoing radiation is established extremely rapidly. A black hole is not a box that holds information for billions of years. It is a mixer that processes information and returns it, scrambled beyond recognition, but in principle present, almost immediately. This is a beautiful picture. It is also, at present, a picture whose microscopic mechanism is not understood. We know that if unitarity holds, scrambling must occur. We do not know the physical process by which the information that fell into the black hole gets encoded in the Hawking radiation. We do not know whether this encoding happens at the horizon, near the singularity, or somewhere in between. We do not know whether it requires modifications to quantum field theory, or modifications to general relativity, or both, or something entirely different. The scrambling picture tells us that information emerges, but does not tell us how. The problem is not merely theoretical. It is operational. If information is scrambled in the Hawking radiation, then a hypothetical observer who collects all the Hawking radiation from an evaporating black hole can, in principle, reconstruct the quantum state of everything that fell in. But in principle, here means with access to an amount of computational resources that grows exponentially with the black hole entropy. The number of quantum operations required to decode the scrambled information from the Hawking radiation is approximately 2 to the power of s, where s is the Bekenstein-Hawking entropy. The information is unrecoverable in any practical sense. But the distinction between preserved and unrecoverable is precisely what the information paradox is about, and it is a distinction with profound implications for fundamental physics, even when it has no practical consequences. The problem is not merely theoretical. The problem is the mechanism. Even if we assume, as most physicists do today, that information is somehow preserved in black hole evaporation, we have no accepted, agreed upon, mathematically rigorous description of how this happens. Where does the information go? When does it come out? How is it encoded in the outgoing Hawking radiation? These questions have no consensus answers, and the various proposed answers each come with their own profound difficulties. The most successful framework for thinking about the information paradox is the gauge-gravity duality, also called the ADS-CFT correspondence, anti-de Sitter space, or conformal field theory correspondence. This is a conjecture enormously well supported by evidence, but not proven, proposed by Juan Maldacena in 1997, that a theory of gravity in a space-time with anti-de Sitter geometry is exactly equivalent to a quantum field theory without gravity, living on the boundary of that space-time. The two descriptions, one involving gravity in the bulk, one involving quantum field theory on the boundary, describe the same physics in different languages. The duality maps the difficult problems of quantum gravity inside the bulk to more tractable problems in the boundary quantum field theory. Crucially, the boundary quantum field theory is unitary by construction. If the duality is correct, the gravitational theory in the bulk must also be unitary, and therefore, in this framework, black hole evaporation is unitary. Information is preserved. The correspondence essentially provides a proof by duality that information is not destroyed. This is why most theoretical physicists today believe information is preserved. Not because anyone has directly described the mechanism in the bulk gravitational theory, but because the duality argument is so compelling that it amounts to a proof of unitarity by the back door. But the duality has a serious limitation for this purpose. It works in anti-de Sitter spacetime, which has a specific negative cosmological constant, a space that curves back on itself like a hyperbolic surface, with a well-defined boundary where the conformal field theory lives. The universe we live in has a positive cosmological constant. It is de Sitter space, expanding exponentially. Anti-de Sitter and de Sitter spacetimes are, in a real sense, opposites. The ADS-CKFT correspondence has not been rigorously extended to de Sitter spacetime, and it is not clear whether such an extension is possible. We're using a result derived in a spacetime that does not describe our universe to argue about the physics of black holes in our universe. This is a significant gap, and it is not always acknowledged as clearly as it should be. Even within ADS-C50, the mechanism by which information is preserved remains deeply unclear. There is a theorem in quantum information theory, the Page curve, named after the physicist Don Page, who derived it in 1993, that describes how the entanglement entropy of the Hawking radiation should evolve over the lifetime of a black hole, if the evaporation is unitary. At first, as the black hole radiates and the Hawking photons accumulate, the entanglement entropy increases. The Hawking radiation looks thermal and featureless, just as Hawking's calculation says. But roughly halfway through the evaporation, at the Page time unknown, the entropy should stop increasing and start decreasing as information from the interior begins to leak back out into the radiation, encoded in subtle quantum correlations that are not captured by the thermal approximation. The entropy decreases back to zero at complete evaporation tracing the shape of an inverted V, the Page curve. For decades, nobody could reproduce the Page curve from a calculation in pseudocladamal gravity, the framework of quantum fields in curved spacetime that Hawking used. The Page curve was expected from quantum information theory, an ADS-C50, but deriving it from first principles calculations in the gravitational description seemed impossible. Then, in 2019, a series of papers by Ahmed Al-Mahiri, Netta Engelhardt, Donald Morolf, Henry Maxfield, and Jeffrey Pennington, building on earlier work and using a technique called the island formula, demonstrated a calculation in the gravitational description that does reproduce the Page curve. The island formula involves a modification of the entropy calculation that includes contributions from regions called islands, specific regions inside the black hole that, when included in the entropy calculation, produce the correct Page curve. The island formula result was widely celebrated as a breakthrough, and in a limited technical sense it is, but it is not a resolution of the information paradox. It is a demonstration that the Page curve can be reproduced in certain simplified models using certain calculational techniques, without providing a clear physical picture of where the information is, how it gets out, or what the microscopic mechanism of its transmission is. The islands themselves are mysterious objects. They appear in the calculation, they produce the right answer, but their physical meaning is deeply contested. Some physicists view the island formula as pointing toward a new, correct description of black hole interiors. Others view it as a sophisticated approximation whose domain of validity is not yet understood. The debate continues, with the same intensity and the same lack of resolution that has characterized the information paradox since 1976. There is another proposed resolution that is more radical and in some ways more disturbing: black hole complementarity. Proposed by Leonard Susskind, Laris Thorlacius, and John Uglum in 1993, black hole complementarity attempts to resolve the apparent contradiction between unitarity and the classical description of the black hole interior by invoking a form of observer-dependent reality. In the complementarity picture, there are two valid descriptions of what happens during black hole evaporation, and they are mutually exclusive. No single observer can ever witness both. An infalling observer crosses the event horizon smoothly and experiences normal physics inside. A distant observer never sees the infalling observer cross. Instead, from the distant perspective, the infalling matter piles up at the horizon, is scrambled by the Hawking process, and re-emitted as radiation, with information preserved. Both descriptions are valid. Neither contradicts the other, because the two observers can never compare notes. The infalling observer cannot send a signal back out, and the information from inside can never reach the distant observer while the infalling observer is still alive. The apparent contradiction is dissolved by noting that it can never be observed. This is a beautiful argument, and it was widely influential for a decade and a half. Then, in 2012, Ahmed Al-Mahiri, Donald Morolf, Joseph Polshinsky, and James Sully published a paper that broke it. Their argument, called the AMPS argument, after their initials, or the firewall paradox, demonstrated that black hole complementarity cannot be maintained without violating one of three foundational principles: unitarity, the equivalence principle, the principle from general relativity that freely falling observers experience no local effects of gravity, and that the event horizon is locally indistinguishable from flat space, or the validity of effective field theory, quantum field theory and curved spacetime outside the horizon. You cannot keep all three. One must go. The AMPS argument goes as follows. By the page time, halfway through the black hole's evaporation, the early Hawking radiation and the late Hawking radiation are entangled by the requirements of unitarity. The late radiation must be entangled with the early radiation to ensure the quantum state of the total system is pure. But simultaneously, for the equivalence principle to hold at the horizon, for the infalling observer to experience nothing special, the late radiation must be entangled with modes just inside the horizon. In quantum mechanics, however, a quantum system cannot be maximally entangled with two different things simultaneously. This is called the monogamy of entanglement. Entanglement is not shareable. A system that is maximally entangled with system A cannot also be maximally entangled with system B. But the requirements of unitarity and the equivalence principle together demand exactly this, that the late radiation be maximally entangled with both the early radiation and the interior modes simultaneously. This is impossible. Something must give. If unitarity holds, the late radiation is entangled with the early radiation and cannot be entangled with the interior modes. This means the correlations between the infalling observer and the radiation at the horizon are severed. The state at the horizon is not the smooth vacuum that the equivalence principle requires. It is a high energy state, a state from which correlations have been violently cut. The infalling observer does not fall smoothly through the horizon. Instead, they hit a wall of high energy radiation, a firewall, at the horizon. The equivalence principle fails. The inside of the black hole, as a smoothly connected region of space-time, does not exist. The horizon is not a surface you cross. It is a surface where you are incinerated. The firewall paradox is not a proof that firewalls exist. It is a proof that something must break. Ere the unitarity and information is destroyed, or the equivalence principle and you are burned at the horizon, or effective field theory, and we cannot trust the secular calculation even far from the horizon. All three options are catastrophic for existing physics. Unitarity is the backbone of quantum mechanics. The equivalence principle is the foundation of general relativity. The validity of effective field theory outside the horizon is the assumption underlying every calculation made about Hawking radiation and black hole physics for 50 years. All three cannot be simultaneously true. Almeri, Rolf, Polchinski, and Sully had turned the information paradox from a philosophical puzzle into a sharp, inescapable logical trilemma. The response from the theoretical physics community was immediate and enormous. Within months of the AMPS paper, hundreds of responses and proposed resolutions appeared. Susskind argued that the firewall was an artifact of incorrectly applying quantum information theory to gravity. Hawking proposed a modified version of the event horizon, a metastable boundary. And it would not have the firewall problem, but would require redefining what an event horizon is. Maldacena and Susskind proposed a radical resolution involving wormholes, the ER equals EPR conjecture, suggesting that entangled particles are always connected by microscopic wormholes, and that the entanglement between the infalling observer and the Hawking radiation corresponds to a wormhole connecting the interior and the exterior of the black hole. This conjecture, if correct, would fundamentally change our understanding of both entanglement and space-time geometry. It would mean that quantum entanglement and space-time topology are deeply connected, that entanglement is, in some sense, what space-time is made of. The ER equals EPR conjecture is speculative, but it has been extraordinarily productive. It connects to a broader program called IT from qubit. The idea that space-time geometry emerges from quantum entanglement, that the fabric of space is woven from the quantum correlations between microscopic degrees of freedom. This idea, pursued by Maldacena, Van Ramsdonk, Brahim Swingle, and many others, suggests that the very connectivity of space-time, the fact that distant regions are connected by smooth space-time geometry rather than being disjoint, corresponds to the entanglement between the quantum degrees of freedom describing those regions. I haven't seen so, but when you disentangle two systems, the spatial connection between their corresponding space-time regions dissolves. Space-time literally tears apart when entanglement is severed. This is not a fringe idea. It is one of the most actively pursued research programs in quantum gravity today. And if it is correct, it has a profound implication. Space-time is not fundamental. It is emergent. The smooth, continuous four-dimensional space-time of general relativity, the arena within which all of physics has been formulated for a century, is not the ultimate description of reality. It is a collective, approximate description that emerges from an underlying quantum mechanical substrate in the same way that the smooth flow of a fluid emerges from the chaotic motion of individual atoms. There is no space. There are no distances. There is only entanglement, and space-time is what entanglement looks like from far enough away. If this is true, the singularity inside a black hole is not a place where space-time ends. It is a place where the space-time description ceases to be valid, where the collective, emergent description breaks down, and the underlying quantum mechanics must take over. The singularity is not real. It is an artifact of applying an approximate, emergent description in a regime where it is not applicable. The real physics at the center of a black hole is quantum mechanical, discrete, finite, and the singularity is the emergent description's way of pointing at its own breakdown. This is a beautiful idea. It is also completely unconfirmed. We do not know how to calculate what happens at the center of a black hole in the quantum mechanical description that would replace the geometric one. We do not know whether space-time really is emergent from entanglement in a complete, rigorous sense, or only in certain simplified models. We do not know whether the ER-EPR conjecture is literally true or merely a useful heuristic. These are active research questions, not settled conclusions. Meanwhile, the observational astronomy of black holes has been proceeding with extraordinary success, largely decoupled from the theory of graces and steep size of losses of compound without time. In 2019, the Event Horizon Telescope, the collaborative effort that combined 8 radio observatories into an Earth-sized interferometer, released the first image of a black hole, the supermassive black hole at the center of the galaxy M87. 6.5 billion times the mass of the Sun, 55 million light-years away. The image showed a bright ring of emission, synchrotron radiation from hot plasma orbiting the black hole, with a dark central region corresponding to the black hole shadow. The region where the black hole's gravity captures photons and prevents them from escaping to the observer. The shadow's size and shape were consistent with general relativity's predictions to within the measurement uncertainty. In 2022, the Event Horizon Telescope released its image of Sagittarius A.Set, the supermassive black hole at the center of our own Milky Way. SCRA A* is 4 million solar masses and 26,000 light-years away, far closer than M87, but far less massive, with a horizon that appears smaller on the sky despite its proximity. The challenge of imaging Esgrar A star was greater than M87 because the plasma near Esgrar A star varies rapidly. The orbital timescale for plasma at the innermost stable orbit is only a few minutes, compared to several days for M87. So the source changes structure while the observations are being taken. The image required sophisticated algorithms to reconstruct an average image from data taken over many hours, accounting for the variable source structure. The result was another glowing ring with a dark center, again consistent with general relativity. These images are not merely beautiful. They are precision tests of general relativity in the strong field regime, the regime where the gravitational field is so strong that the curvature of space-time is a dominant effect, not a small perturbation. The size of the black hole shadow, the shape of the photon ring surrounding it, the asymmetry of the brightness distribution, all of these encode specific predictions of general relativity. They have been measured, and they are consistent with the theory. General relativity works at the event horizon. It works in the strong field regime. It is not failing where we can test it. The failure is deeper. It is the failure at the singularity, which we cannot test with any existing instrument. And it is the conceptual failure of the information paradox, which is not a failure of observational prediction, but a failure of theoretical consistency. The problem is not that general relativity gives the wrong answer for the size of the shadow. It is that general relativity and quantum mechanics, combined, give contradictory answers for what happens to information over the lifetime of a black hole. These two frameworks, each correct in its own domain, produce a logical contradiction when applied together to the same system. The contradiction is not an anomaly, it is a feature. It is telling us that something fundamental is missing from our understanding of physics. The detection of gravitational waves from merging black holes, which began on September 14, 2015, a date that will stand as one of the most important in the history of science, the first direct detection of gravitational waves, confirmed by the LIGO interferometers in Hanford, Washington and Livingston, Louisiana, opened another window on black hole physics. The signal, designated GW150914, was produced by the merger of two black holes approximately 29 and 36 solar masses, located roughly 1.3 billion light-years away. The merger produced a final black hole of approximately 62 solar masses. The missing mass, about 3 solar masses, roughly 6 times the mass of all the planets in our solar system combined, was converted to gravitational radiation and radiated away in a fraction of a second. The peak power of this radiation, the rate of energy emission at the moment of merger, was approximately 3.6 times 10,499 watts. For comparison, the total luminosity of the observable universe, all its stars, all its galaxies, all their combined light output, is approximately 5 times 10,004 watts. The gravitational wave emission from GW150914 at its peak outshone the visible light output of the entire observable universe by a factor of roughly 7 million. We felt it as a strain of 10⁻²,000, a distortion of space-time so tiny that the arms of the LIGO interferometers were displaced by less than 1/10,000th the diameter of a proton. Detected by lasers, by mirrors suspended on 4-stage pendulums, isolated from seismic noise, by photodetectors counting individual photons. The engineering required to detect a displacement 1,000 times smaller than an atomic nucleus across a 4-kilometer baseline is not merely impressive, it is one of the greatest technological achievements in human history. And it worked. The LIGO detectors themselves deserve a moment of attention because they represent a triumph of human ingenuity operating at the absolute limits of what is physical measurable. Each detector is an L-shaped interferometer with arms 4 kilometers long. A laser beam is split at the junction of the L, sent down both arms, reflected off mirrors at the ends, and recombined at the beam splitter. In the absence of a gravitational wave, the two beams travel exactly the same distance and interfere destructively. The recombined beam is dark. When a gravitational wave passes, it stretches one arm and compresses the other, changing the relative path length by a tiny amount, and the recombined beam brightens slightly. By monitoring the brightness of the recombined beam, the detector measures the strain, the fractional change in arm length caused by the passing wave. A strain of 10-21 means one arm changes length by 10-21 times 4 kilometers, which is approximately 4 times 10-1008 meters, about 4 attometers, or 1/10,000th the diameter of a proton. To achieve this sensitivity required decades of technological development. The mirrors must be suspended in isolation systems that reduce seismic noise by 10 orders of magnitude at the signal frequencies. The quadruple pendulum systems damp vibrations so effectively that thermal noise in the mirror coatings, which causes the mirror surfaces to jitter by tiny amounts due to random thermal motion, became the dominant noise source at some frequencies and required the development of specialized mirror coatings with extraordinarily low mechanical dissipation. The laser power was increased over successive generations of the detector to reduce quantum shot noise, the statistical fluctuations in photon counting, and then squeezed light technology was introduced to reduce the quantum noise below the standard quantum limit. Each generation of improvement pushed the detector sensitivity closer to the fundamental limits set by quantum mechanics itself. The detectors are not just instruments. They are, in a sense, a probe of the boundary between classical and quantum physics, operating in a regime where quantum effects in the mirrors and the laser light are critical factors in their sensitivity. Since GW 150914, LIGO and its international partners, the Virgo detector in Italy, the Kagra detector in Japan, have detected dozens of merging compact objects, black holes merging with black holes, neutron stars merging with neutron stars, and black holes merging with neutron stars. Each detection is a test of general relativity in the strong field, high velocity, highly dynamic regime. Each detection has been consistent with the theory. The catalogue of gravitational wave events has become a population study, a census of compact objects in the universe, telling us about the mass distribution of black holes, the rate of mergers, the alignment of spins, the distribution of merger events across cosmic time. It has revealed unexpected features, black holes and the mass gap between 65 and 130 solar masses, where they should not form from ordinary stellar evolution, because the progenitor stars are disrupted by pair instability supernovae before they can collapse. Black holes merging with objects of uncertain identity in the neutron star to black hole mass gap, and mergers producing remnants that may be intermediate mass black holes. The gravitational wave sky is richer and stranger than the pre-detection models predicted. General relativity describes the geometry of black hole mergers with breathtaking precision. The waveform, the shape of the gravitational wave signal as a function of time, is a direct imprint of the space-time geometry of the merging system. In the measured waveforms match the predictions of numerical general relativity simulations to within the measurement precision. The ring-down phase of the signal, the period immediately after merger, when the newly formed black hole is settling into its final Kerr geometry. Oscillating at its characteristic quasi-normal mode frequencies has been used to test the no-hair theorem, the prediction of general relativity that a black hole is completely characterized by just three parameters: mass, spin, and electric charge, and real astrophysical black holes are electrically neutral, so just mass and spin. The tests are consistent with the no-hair theorem. Black holes, as far as we can measure, are the simple objects that general relativity says they are. The no-hair theorem itself, proven in the 1970s by Werner Israel, Brandon Carter, David Robinson, and Stephen Hawking, is one of the most elegant results in general relativity and one of the most troubling for quantum mechanics. The theorem states that two black holes with the same mass, spin, and charge are completely indistinguishable, no matter what collapsed to form them. A black hole formed from the collapse of a massive star, and a black hole of identical mass and spin formed from the collapse of an equal mass of antimatter are, in classical general relativity, absolutely identical. The geometry of their spacetimes is the same. Their gravitational fields are the same. Every measurable property from outside is the same. The information about what formed them, the quantum state, the composition, the history, is entirely absent from the external description. Wheeler summarized this with his famous aphorism, "Black holes have no hair." The hair, in this metaphor, is the detailed information about what the black hole is made of. A bald head looks the same, regardless of how its owner lost their hair. A black hole looks the same, regardless of what fell in to form it. The hair, the information, is gone. In classical general relativity, this is simply a property of the solution. Black holes are described by the Kerr-Newman family of solutions, parameterized only by mass, spin, and charge. There are no other classical parameters. The no-hair theorem is a theorem about classical solutions. It does not, by itself, say that information is destroyed. Classical physics is deterministic. In principle, if you knew the initial conditions of the entire universe, you could predict its future exactly, and information is preserved in the classical sense because the equations of motion are reversible. Even in classical general relativity, the information is not destroyed, it is inside the black hole, encoded in the singularity, inaccessible to external observers, but not non-existent. The problem is quantum mechanics. In quantum mechanics, the state of a system must be a well-defined quantum state, a vector in a Hilbert space, with definite quantum mechanical probabilities for all observables. The evolution of this state must be unitary. It must preserve the total probability and the quantum information. If you start with a pure state and the evolution is unitary, you end with a pure state. But if two different initial pure states, two different configurations of collapsing matter, produce the same black hole, same mass, spin, charge, then, when the black hole evaporates and produces the same thermal Hawking radiation, you have two different initial pure states mapped to the same final state. That is not possible in unitary quantum mechanics. A unitary map cannot map two different states to the same state. It is one-to-one, by definition. Something must give. This is the quantum version of the no-hair paradox. Not merely that we cannot tell from outside what fell in, that is a statement about our ignorance, but that two different quantum states produce the same final state after evaporation, that is a statement about physics. It says quantum evolution is not unitary. It says information is destroyed. And it says the no-hair theorem, however elegant, is incompatible with quantum mechanics. at a fundamental level. The quest for a quantum theory of gravity has produced multiple serious candidates, each with different approaches to resolving the information paradox and the no-here problem. String theory, the most developed candidate, approaches the problem through a microscopic description of black holes as configurations of strings and other extended objects. In 1996, Andrew Strominger and Kamran Vafa, working within string theory, computed the Bekenstein-Hawking entropy of a specific class of extremal black holes at the boundary between those that would evolve further and those that are stable, by counting the microscopic string states corresponding to those black holes. They found exact agreement with the Bekenstein-Hawking formula, S equals A divided by 4. The entropy counting worked. The microscopic string states numbered exactly as many as the Bekenstein-Hawking formula predicted. For the first time, the entropy of a black hole had a microscopic derivation from a specific quantum theory. Strominger-Vafa calculation is a landmark result, but it applies to a highly specific and non-generic class of black holes, extremal, supersymmetric black holes, in a 10-dimensional string theory compactification. Real astrophysical black holes are not extremal and not supersymmetric. The calculation has been extended to near-extremal black holes and to some non-extremal cases with good results, but the full microscopic description of a generic, astrophysically realistic black hole in string theory remains for more than 25 years. Loop quantum gravity takes a different approach, quantizing spacetime geometry directly rather than working with strings. In loop quantum gravity, the smooth continuum of general relativistic spacetime is replaced by a discrete structure, a spin network, a graph whose nodes represent quanta of volume and whose edges represent quanta of area, with the geometric quantities taking discrete values that are multiples of the Planck area and Planck volume. The area of the event horizon, in this framework, is a sum of area quanta contributed by the edges of the spin network that puncture the horizon. The number of ways these quanta can be arranged, the number of distinct spin network configurations consistent with a given total area, is the microscopic source of the Bekenstein-Hawking entropy. The calculation, performed by Carlo Rovelli, Kirill Krasnow, and collaborators in the 1990s, gives a result consistent with the Bekenstein-Hawking formula up to an undetermined numerical factor called the Barbero-Immersi parameter. As the kind of civilization functions go, Koren could not stop telling it, but telling whether will allow it to try. After which, the matter abounds, and the geometry continues into a new phase. The singularity is replaced by a high-density, finite region where quantum geometry effects dominate. This eliminates the breakdown of physics at the singularity. Physics continues, in the loop quantum gravity description, through the region that would be the singularity in the classical theory. What emerges on the other side is less clear, the subject of ongoing research, but the singularity itself, as a termination of physics, is eliminated. Neither string theory nor loop quantum gravity has been confirmed experimentally. The characteristic scales at which quantum gravity effects become important, the Planck scale, are at energies roughly 10 to the power of 15 times higher than those accessible to the Large Hadron Collider, the most powerful particle accelerator ever built. Direct experimental tests of quantum gravity at the Planck scale are not conceivable with any technology foreseeable in the next century, or perhaps ever. The hope for testing quantum gravity experimentally rests on finding indirect signatures in the CMB and the spectrum of Hawking radiation from primordial black holes, if they exist, in subtle violations of Lorentz invariance predicted by some models, in the precise properties of gravitational wave signals from merging black holes, or in some discovery we have not yet imagined. The situation is frustrating for an empirical science. Our best candidates for quantum gravity make predictions that are not yet testable. But this is not unusual in the history of physics. General relativity was proposed in 1915 and confirmed by the observation of light bending during a solar eclipse in 1919. The prediction of gravitational waves was made in 1916 and confirmed in 2015, 99 years later. Patience is a scientific virtue. The universe will eventually provide the data. But here is the tension that lies at the heart of why black holes terrify physicists. The no-hair theorem says that a black hole has no hair, no detailed information about what fell in to form it beyond mass and spin. All other information is lost. But information in quantum mechanics cannot be lost. The no-hair theorem is a statement of information loss. The unitarity of quantum mechanics is a statement of information preservation. They are not compatible. General relativity says black holes are bald. Quantum mechanics says they must be covered, however subtly, in a kind of quantum hair, in some encoding of the quantum state of the matter that formed them, hidden somewhere in the Hawking radiation or in the structure of the quantum state of the horizon. But we have no observation of such quantum hair. We have no theory that clearly predicts it. We have only the logical necessity that it must exist if unitarity is to be preserved, and the complete absence of a mechanism for it. There is one more theoretical development, so recent and so disturbing that it deserves careful attention: the wormhole calculus. In 2019, building on the Island formula results, researchers made a calculation in the gravitational path integral, a mathematical tool that sums over all possible space-time geometries to compute quantum gravitational effects, and found that the correct page curve is reproduced when you include contributions from wormhole geometries connecting different parts of the space-time. These wormhole contributions are not physical wormholes in the science fiction sense, not tunnels you could travel through. They are saddle points of the gravitational path integral, contributing to the calculation in the way that quantum tunneling contributes to chemical reactions or radioactive decay. Their contribution produces the page curve. Without them, the page curve does not emerge. This is extraordinary, but it creates a new puzzle. In quantum mechanics, the partition function, the mathematical object that encodes all thermodynamic properties of a system, is smooth. It varies continuously with parameters. But in the gravitational path integral, with wormhole contributions, there appear to be corrections that make the partition function factorize into a sum of discrete terms corresponding to different baby universes that can pinch off from the main spacetime and carry information away. This suggests, though the argument is subtle and contested, that the gravitational path integral is not computing the properties of a single theory, but rather averaging over an ensemble of theories, each with slightly different random couplings. If this is right, it means that the gravitational path integral does not describe a single definite quantum mechanical theory. It describes the average behavior of many theories. The precise quantum state of any given black hole would not be determined by any calculation we can do. It would be random, drawn from the ensemble. This possibility that quantum gravity is not a theory but an ensemble would be, if confirmed, one of the most radical conclusions in the history of physics. It would mean that the universe has no precise microscopic description, that the question, what is the exact quantum state of the black hole, has no definite answer, not because we are ignorant of the answer, but because there is no fact of the matter. The universe at its deepest level would be fundamentally random, not just in the quantum mechanical sense, where outcomes are random but probabilities are well defined, but in the sense that even the theory describing it is random. This is not a conclusion that most physicists find comfortable, but it is one that the mathematics of the wormhole calculus appears to point to, and taking the mathematics seriously is what physics is. These are the things that terrify physicists about black holes. Not the darkness, not the tidal forces, not the singularity as a physical threat. The terror is intellectual. It is the terror of looking at two frameworks that have been tested to extraordinary precision and finding that when you put them in the same room, when you ask them both to describe the same physical process, the birth and death of a black hole, they contradict each other in a way that cannot be papered over, cannot be finessed, cannot be resolved by adding a small correction term. One of them, or both of them, must be wrong. Or both of them must be subsumed into something larger and more complete, something we do not yet have, something whose shape we can barely see by looking at the shadows its absence casts on the theories we do have. But there is another dimension of black hole terror that operates not in the abstract realm of information paradoxes, but in the very concrete realm of the observable universe, the terror of what black holes do to their surroundings. The terror of the active black hole, the terror of the quasar. When matter falls toward a black hole, it rarely falls straight in. It carries angular momentum, a small amount of sideways motion, and this angular momentum prevents it from falling directly to the center. Instead, the infalling matter spirals inward, conserving its angular momentum, and forms a disk, the accretion disk. The accretion disk around the black hole is one of the most energetically extreme environments in the universe. As matter spirals inward through the disk, it loses gravitational potential energy. In a simple Newtonian calculation, the energy of a circular orbit is proportional to the inverse of the radius, and as the radius decreases, the energy decreases. The matter must lose energy to spiral inward. This energy goes into heat. The disk heats up as matter spirals in. The temperature in the inner regions of the disk, closest to the event horizon, can reach tens of millions of Kelvin for a stellar mass black hole, and hundreds of thousands of Kelvin for a supermassive one. The disk glows in hard X-rays for stellar mass black holes in binary systems, in softer X-rays and ultraviolet for the supermassive black holes powering quasars. The efficiency of accretion, the fraction of the infalling matter's rest mass energy that is converted to radiation before the matter crosses the horizon, depends on the geometry of the orbit. For a Schwarzschild black hole, non-rotating, the innermost stable circular orbit, the closest orbit from which matter can spiral in and still be stable, below which all orbits plunge directly into the black hole, is at 3 times the Schwarzschild radius. The efficiency of accretion from this orbit is approximately 5.7% of the rest mass energy. For a maximally rotating Kerr black hole, the innermost stable circular orbit is much closer to the horizon, and the efficiency can be as high as 42% of the rest mass energy. Compare this to nuclear fusion with an efficiency of 0.7%. Accretion onto a rotating black hole is 60 times more efficient than nuclear fusion. It is the most efficient energy release mechanism that physics permits, short of matter-antimatter annihilation. Quasars, the most luminous, persistent objects in the universe, are powered by this process. Supermassive black holes accreting at high rates, releasing energy with 10 to 40% efficiency, outshining entire galaxies of 100 billion stars combined. The most powerful quasars have luminosities of approximately 10,141 watts, about 25 trillion times the luminosity of the Sun, and roughly 10 million times the luminosity of the entire Milky Way galaxy. This energy comes from a region roughly the size of our solar system, a few light hours across, at most, corresponding to the accretion disk around a billion solar mass black hole. The energy density in this region exceeds anything else in the known universe, and it is released not quietly, but in the most dramatic fashion conceivable, in jets. Relativistic jets are among the most spectacular phenomena in astrophysics. Collimated beams of plasma, moving at 99.9% of the speed of light, or higher, launched from the polar regions of accreting black holes, extending for hundreds of thousands or millions of light years, from a compact object, a few light hours across, to a jet that spans a distance comparable to the distance between galaxies. The jet from M87, the same galaxy whose central black hole was imaged by the Event Horizon Telescope, extends for approximately 6,000 light years, visible from radio wavelengths to X-rays. Moving at superluminal apparent speeds due to a relativistic projection effect that makes components of the jet appear to move faster than light when observed from our line of sight. They are not actually moving faster than light. The apparent superluminal motion is an illusion of geometry and the finite speed of light. When pointed at Earth, the jets of active black holes produce blazars, some of the brightest and most violently variable objects in the gamma-ray sky, visible across billions of light years. The mechanism by which jets are launched is not fully understood. The leading model involves the Blamford-Znaeck process, in which the rotating spacetime around the Kerr black hole, the frame dragging of spacetime by the spinning black hole's angular momentum, a consequence of general relativity, acts as a kind of electromagnetic generator. Magnetic field lines, threading the black hole's event horizon, are wound up by the rotating spacetime, creating a helical magnetic structure that extracts rotational energy from the black hole itself and channels it into the jet. In this picture, the jet is powered not by the accreted material, but by the rotational energy of the black hole, the spin that the black hole has accumulated over its lifetime of accretion. The Blamford-Znaeck process is elegant, and numerical simulations of magnetically arrested accretion flows have reproduced jet-like structures broadly consistent with observations. But the detailed physics of jet launching, how the energy is channeled, how the jet remains collimated over millions of light years, what determines the jet's power and direction, remains an active research problem. What is not in question is the impact of these jets on their environments. The jets of powerful radio galaxies and quasars inject enormous amounts of energy into the hot gas that fills the space between galaxies and galaxy clusters, the intracluster medium. This energy input, called AGN feedback, for active galactic nucleus feedback, heats the intracluster medium, suppresses cooling, and prevents the runaway condensation of gas that would otherwise produce star formation rates far higher than observed. The supermassive black holes at the centers of galaxies are not merely passive objects sitting at the bottom of their host galaxy's gravitational wells. They are active participants in the regulation of galaxy growth, a feedback loop connecting the smallest compact objects to the largest structures in the universe. The black hole shapes the galaxy feeds the black hole. The relationship is symbiotic, violent, and billions of years old. We see this in the tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy's stellar bulge, the old, slowly evolving central region of the galaxy. The black hole mass correlates with the bulge velocity dispersion, how fast the stars in the bulge are moving, with a scatter so tight that it is called the M-sigma relation. A galaxy with a faster moving stellar bulge has a more massive central black hole, with an accuracy of better than a factor of 2 over 5 orders of magnitude in black hole mass. The black hole, which occupies a region millions of times smaller than the galaxy itself, has somehow regulated the growth of the galaxy's entire stellar bulge. The mechanism of this coevolution, how a black hole accreting at the center of a galaxy can affect star formation in a region 1,000 times larger, involves the jets, the winds, from the accretion disk and the radiation pressure from the luminous nucleus, all of which can heat and expel gas from the galaxy, shutting off the fuel supply for future star formation. The black hole, in regulating its own food supply, regulates the galaxy around it. Stephen Hawking, in his later years, described the information paradox as his greatest contribution to physics, greater, in his estimation, than the singularity theorems, greater than the area theorem for black holes, greater than his work on cosmology. He said this not because he solved it, but because he believed its resolution, when it came, would require a fundamental revision of our understanding of quantum mechanics, general relativity, or both. He believed he had found the crack in the foundations of physics. 40 years later, the crack is still there, and we have widened it considerably, but we have not yet laid the new foundation. That new foundation, quantum gravity, is the most sought-after theory in fundamental physics. String theory, loop quantum gravity, causal dynamical triangulations, causal set theory, and a dozen other approaches each claim to be candidates. Each has adherents among serious physicists, and none has been confirmed by experiment. String theory, the most developed candidate, provides the ADS-C50 correspondence and has produced the most direct insights into the information paradox, but he's also produced a landscape of approximately 10,550 consistent vacuum states, each corresponding to a possible universe with different physical constants, and no clear principle for selecting which one we live in. The landscape connects string theory to the inflationary multiverse and to the anthropic principle in ways that some physicists find elegant and others find a disaster for scientific predictability. Loop quantum gravity describes a discrete, granular spacetime, space as a network of quantum geometrical structures called spin networks, with geometry quantized in units related to the Planck length, and eliminates the singularity at the center of a black hole by replacing it with a quantum bounce, a region of extreme but finite density where the geometry of spacetime is granular and the classical description breaks down. But loop quantum gravity has not yet produced a convincing description of Hawking radiation or addressed the information paradox with the same depth as string theory approaches. The black hole is the laboratory where quantum gravity will be tested. Not because we can build an instrument sensitive enough to see Hawking radiation from a real astrophysical black hole, we cannot, with any technology conceivable in the near future, but because any complete, consistent theory of quantum gravity must be able to describe what happens when a black hole forms and evaporates, must resolve the information paradox, must explain the page curve, must account for the firewall or explain why there is no firewall, must say what happens at the singularity and why. These are not optional features of a complete quantum gravity theory. They are mandatory. Any theory that cannot address them is not a theory of quantum gravity. It is a partial theory, a candidate, a sketch. The black hole sets the exam question for quantum gravity, and no one has yet passed. This is in the deepest sense why black holes terrify scientists, not as objects, as problems, as logical structures that sit quietly at the intersection of every great theory we have and announce with mathematical certainty that our understanding is incomplete. The black hole is the universe's way of telling us that the physics we have is not the final physics, that something is missing, something essential, something foundational. And we are close enough to the answer to feel its shape, but not yet close enough to see it clearly. The event horizon of a black hole is an edge of knowledge as much as an edge of space-time. Beyond it, from the outside, nothing comes back. But the information about what lies beyond, the physics that must exist on the other side of our current understanding, is real, and it is coming. It is encoded, somehow, in the outgoing radiation, in the subtle quantum correlations that Hawking's thermal approximation missed, in the islands and the wormholes and the entanglement structure of space-time itself. The answer is out there. It is in the mathematics, waiting to be found, as it has always been, when physics reaches its own horizon and finds not an ending, but an edge beyond which the next physics begins. You are alive in the moment before that edge is crossed. You are watching the most brilliant minds in physics work in real time on the hardest problem physics has ever faced. The equations are on the whiteboard. The debates are in the journals. The disagreements are genuine and profound and productive. The answer is not yet known, but it is being found, piece by piece, argument by argument, calculation by calculation. The way every great answer in the history of science has been found, slowly, and then suddenly, by people who refuse to accept that the boundary of what is known is also the boundary of what can be known. The black hole waits. It does not impart its secrets easily. It has been keeping them for the entire history of the universe. But it has been keeping them in plain sight, written in the mathematics of physics, in the temperature of its radiation, in the shape of its shadow, in the sound of space-time ringing after a merger. We have the photograph, we have the waveform, we have the page curve, we have the paradox, sharp and clear, with all its contradictions mapped in detail. What we do not yet have is the resolution, but the resolution is closer than it has ever been. And the moment it arrives, the moment someone writes down a consistent theory that preserves information, resolves the firewall, explains the page curve from first principles, and predicts the physics of the singularity, will be one of the most extraordinary moments in the history of human knowledge. The day physics stops being terrified of black holes and starts, finally, to understand them. That day has not come. But it is being worked on, right now, by people who look at the event horizon and see not a limit, but a question